So for this example problem, we are looking at one of Mars's moons, Phobos, and its orbit around Mars. And we've got the masses of both Mars and its moon, Phobos. And we know the gravitational force between the two, and now we want to find how far apart they are. So here I've got Mars, I've got Phobos. Phobos orbits around Mars, okay? We want to find the distance, and we call distance the radius because the distance from the center of mass for both objects will end up being the radius of this circle in the circular path if we were to rotate Mars around, or Phobos around Mars, or even vice versa. So even though it is a distance between the two, we call it the radius because it ends up becoming the radius of the circle for the circular path. Okay, assuming this is a perfect circle. So here we've got the mass of Mars, which is 6.4 times 10 to the 23rd kilograms. We've got the mass of Phobos, which has a mass of 9.6 times 10 to the 15th kilograms, which is significantly smaller. And we know that the magnitude of the gravitational force between the two bodies is 4.6 times 10 to the 15th newtons. Okay? And if we go to, or if we write down the equation for gravitational attraction, or Newton's law of gravitational attraction, here we've got Fg is equal to big G, which is a constant, times the mass of my first object, times the mass of my second object, over the distance between the two objects squared. Okay. And in this case, remember, G being a constant, it's kind of a fudge factor when we're solving these problems. Remember, we call that the universal, or the constant, excuse me, of universal gravitation, and its value is a constant value of 6.673 times 10 to the negative 11th Newton meter squared per kilogram squared. Crazy fudge factor, but it will help our units work out and keep everything at the right magnitude. All right. So again, I would give this to you all the time, so you don't have to worry about stressing out about that. Okay, let's go ahead and plug in, or actually we're looking for R. So R equals what? All right. So again, I can swap these two and say that R squared would be, the constant of universal gravitation times m1, m2 over my gravitational force, square root the 2. I get R is equal to the square root of G times m1, m2 over Fg. Okay. Alright, looks like a lot of crazy math. It's really not too bad. So let's plug in what we know. We got that it's the square root of, I'm going to use a pen so that way I don't run out of room. So 6.673 times 10 to the negative 11th Newton meter squared per kilogram squared. Alright, times m1, so the mass of my first object, I'll call it Mars, 6.4 times 10 to the 23rd kilogram, times the mass of my second object, so in this case Phobos, 9.6 times 10 to the 15th kilograms, all over my gravitational force, so 4.6 times 10 to the 15th newtons. Well, go ahead and keep it newtons because I do see I've got newtons in this fudge factor up here. Okay. Solve across the top. We get, so for our numerator, we get R is equal to, let's squeeze this up. All right. I know my units, I'm going to have Newton meter squared divided by kilogram squared, but times kilogram, so both of those will cancel out my kilogram squared. So I know that for my numerator, I'm just going to have Newton meter squared. Okay. Let's go ahead and see what the magnitude of that value would be. So I'm going to do 6.673. Remember, times 10 to the, we're going to use the EE button, so times 10 to the negative 11, close your parentheses, new set, 6.4 times 10 to the 23rd times 9.6 times 10 to the 15th. So my numerator is going to be 4.10 times 10 to the 29th Newton meter squared, divided by 4.6 times 10 to the 15th newtons. I know these newtons will cancel. I'll end up with the square root of something that's a meter squared. Let's go ahead and take these two numbers. I'm going to take my numerator, which I still have in my calculator, and divide it by my denominator, 4.6 times 10 to the 15th. So get 8.91 times 10 to the 13th meter squared. And then I square root that and square root the meter squared. Okay, when I square root meter squared, I'm left with just meters, which is good for a distance. Okay, all right, so I'm going to take a square root of that answer. Ooh. Wow. There we go. All right, so this did not give it to me in scientific notation, but I can put this number in scientific notation pretty easily. So I'm going to write 9.44 times 10 to the 6 meters. Okay. I can put that in kilometers by dividing by 10 to the 3, so it's going to give me, or 9.44 times 10 to the 3rd kilometers. Either way, either one of those works.